All right. So last class we did a redox reaction review. So we covered balancing things in acidic solution and then balancing things in basic solution. The only added step in basic solution being that after we've balanced things with H+, we can add hydroxide to both sides, and on our side that has the H2O, the H pluses, those will turn into H2Os when they react with that OH minus, or at least that's the way that it would work if we were adding them in solution. This is all just theoretical. So this is a faster way. I think it's an easier way of balancing them rather than using the difference in hydrogens between H2O and OH minus to balance things. I think this is a nicer way of doing it. We're just adding one step, and so I think that thing keeps things relatively simple and easy. Now moving on to some more proper electrochemistry stuff. Voltaic cells. Voltaic cells generate electricity. We'll talk about those later. But they work on the principle of electrical current. Electrical current is our flow of electric charge being carried by electrons. So we typically think of electricity flowing in the form of electrons moving through a wire or air or whatever other medium that they might be traveling through. Redox reactions can be used to generate electrical current. For example, in our reaction between zinc metal and copper ion dissolved in aqueous solution, there's a transfer of electrons from the zinc to the copper. And so that results in copper turning into its solid form with no charge, and zinc, since it's lost 2 electrons, picking up a 2 positive charge. This reaction occurs because zinc has a greater tendency to lose electrons. Or donate, or just otherwise get rid of. It's more metallic in character. So the zinc atom transfers 2 electrons to the copper ion, and this might look something like this in solution or in practical application. So we've got a strip of zinc metal that's in a copper 2 sulfate solution, and what's going on is our zinc strip, we've got a lot of zinc here, and we've got copper ions in solution, and so the zinc ions can donate or give electrons to the copper 2 plus ions in solution. That results in our copper atoms, copper solid forms on the zinc strip. And because the zinc has lost electrons, it goes into solution. So that's what this might look like. And we can see also the copper sulfate solution, copper 2 sulfate solution, has lost some of its blue color because of it losing some of those copper atoms, perhaps. Ions, rather. So what we can do with this principle is we can separate the zinc atoms and the copper ions and force the electron transfer to occur through a wire instead of directly. Right, we don't have to have the metals together, we can separate them out. And this is an electrochemical cell. And we have 2 types of electrochemical cells. We've got our spontaneous voltaic cells. Think a battery. Also called a galvanic cell. And these produce electrical current, so that's why it's a battery. And it's a spontaneous chemical reaction. An electrolytic cell requires energy. So this is a non-spontaneous electrochemical cell. And it consumes electrical current. An example of this would be electrolysis, splitting different chemicals in water. For example, you could in theory do this at home if you run electrical current through some water. It's dangerous because you could also produce chlorine gas, which is very bad to breathe, and other things. There's lots of bad stuff that could happen if you do this at home, so don't. Okay, here's a big picture of a voltaic cell. So we've got a lot going on here, so we'll talk through it. First of all, we've got a strip of metal. These are called our electrodes. So we've got a zinc electrode and a copper electrode. So a strip of each metal, that's our electrode. We place it in a solution of its ions. So we've got zinc nitrate and we've got copper 2 nitrate in solution. And these form half cells. We can think of these like half reactions. And someday I'll learn how to space things correctly with writing. Today is not that day. So these are half reactions. Other things that we've got going on, we've got this salt bridge. We'll be talking about that in a bit. The reason that it's up in the air is so that the solutions don't mix. So we've got that salt bridge, and so our solutions are not going to travel up and through that salt bridge, but we have potassium nitrate, and those charged particles will move through that salt solution. We'll learn more about that in a bit. And then because we've separated out the zinc and the copper, we can force our electrons to go through this wire and power like a light bulb or our phone or any other sort of electrical device, since we have a battery here. And the half reactions we've got are separated out up here. Notice that they're both in the same direction, so they're both in the producing electrons direction. Zinc has a greater tendency to ionize, just experimentally, and so its equilibrium is going to lie further to the right. It's going to relatively want to produce electrons. Copper does not want to ionize as much, and so it's going to work in the opposite direction. So zinc is going to produce electrons, and copper is going to use those electrons up and form copper metal. So if we connect these half cells, again, the half cells being basically these half reactions, the zinc and zinc ion, the copper and the copper ion. We've got them in beakers here. So we've got our electrodes and we've got our solutions of the ions. If we connect these two half cells with a wire, then electrons will spontaneously flow from the zinc electrode to the copper electrode. Again, because of this tendency for the electrons to be lost by zinc and to be picked up by copper. The electricity that flows, we've got some terms. We're not going to go super deep into the electricity part of things, but it's good to have a basic understanding of what's going on. So we can think of electrical current as analogous to flowing water, like in a river. So the rate of the electrons flowing is equivalent to the rate of water moving. And our unit of electrical current is the amp, the ampere with the symbol capital A. So this is our unit of how much charge is flowing. So a high current would be a lot of amps. A low current would be not very many amps. And this is with regard to the coulomb. The coulomb is a unit of electrical charge, and we've seen the coulomb before. And our coulomb, our amp rather, is 1 coulomb per second. So it's an amount of charge per second. So some amount of charge per second, it's a coulomb, and so it's a lot of electrons per second. Our water current, the way that rivers flow is driven by a difference in gravitational potential energy. So they will flow, the water will flow downhill. Electrical current is driven also by a potential difference. The potential here talking about energy, a potential energy difference. And we have a measure for potential energy difference. It's a difference in potential energy in joules per unit of charge. And our unit for that is the volt. So a volt is 1V, it's again a unit of potential energy difference, and it's 1 joule per coulomb. So how much, what difference in potential energy do we have per amount of charge? Yeah, that's just what a volt is. It's just a number of joules per coulomb. If we have a large potential energy difference, remember that that's what's causing our electrons to flow. So we can think of a really steep river. If we have a really steep river, then we're going to have a large gravitational potential energy difference. And so we're going to see a really fast rate of flow, or a very strong tendency for electrons to flow. So a steep river flows rapidly, and that's sort of what a large potential energy difference is. So if we have a lot of volts, we're going to have a very rapid flow rate, or we'd expect to have a very rapid flow rate. Or very easily flowing rate. The physics part of this is a little confusing. It's been a long time since I've taken physics, so that's fun. Another thing that we can talk about, another term that we'll be seeing is EMF, electromotive force, not electromagnetic frequency. So electromotive force is another way that we can talk about potential energy difference. The force part of it being force, and the electromotive, electro like electrons and motive like motion, the electron moving force. So we'll see some terms with sub-EMF, and that's what we're talking about here, basically potential energy. I think it's probably more accurate to say that it flows easily rather than rapidly. Some other terms that we've got that are related to, we're kind of all thinking about this in terms of our 2 half cells with the wire that connects them and our little salt bridge. It's kind of the image. We're working up, building up terms that we can use to describe that and talk about like different aspects of that system. And so cell potential or cell EMF is the difference, the potential energy difference between the 2 electrodes, those are the strips of metal, the copper and the zinc, the ones that we were looking at, in a voltaic cell. So this is the volts of the system. How likely is it that electrons will flow, or how easily will the electrons flow? And our cell potential, our E cell, depends on the relative tendency of the reactants to give up electrons or pick up electrons. And so our best case, our highest voltage or highest cell potential, is going to be when we've got something that really wants to give up electrons, high tendency towards oxidation, giving or losing electrons, paired with a substance with a high tendency towards reduction, gaining / winning electrons, gaining / picking up. And it also depends on things like concentration and temperature. But the big part of it is one of our electrodes really likely to give up electrons, and is the other very likely to pick up electrons? If they're both really likely to give electrons, then it's not going to result in as high of a cell potential, because one of them has to receive electrons for one of them to give. So the best case scenario is one of them really wants to get rid of electrons and one of them really wants to pick up electrons. For some reason, Catan is coming to mind. Occasionally there are trades in Catan. I don't like Catan, I don't play Catan, but there's like situations where you're like, I have resources that I would really like to get rid of. Somebody's like, I would really like to get those resources. And so that's a really fast and easy trade. There's probably not a lot of bargaining that has to go on. Might also be like going to the store and you know exactly what you want to get. You're getting there and it's the Futurama meme, you know, take my money. You're not putzing around like, do I want this version or this version? It's just, we're doing it. We know what we want. So our standard cell potential has this 0, that's the standard part, occurs at concentrations of 1 molar or pressures of 1 atmosphere. So it's the same sort of standard conditions that we've seen before, 1 molar, 1 atmosphere. So oftentimes we'll talk about things in terms of their standard cell potential rather than non-standard cell potentials. Okay, thinking about volts and amps, which of these statements best captures the difference between volts and amps? Is it that the volt is a unit that quantifies the difference in electrical potential energy and the amp quantifies flow of electrical current? Is it the other direction, it's the other way, those definitions flipped? Or are they two different units for measuring the same thing? Yeah, it's A. The volt quantifies the difference in electrical potential energy, joules per coulomb, and the amp quantifies the flow of electrical current. How many electrons do we have flowing per second? It's coulombs per second, if I'm remembering correctly. And a coulomb is a number of electrons.
You were saying that amps is like the river, right? The flow?
Yeah, it's like the amount of water that's flowing in the river. A lot of amps, a lot of flow, not a lot of amps, small little stream. You can still have a very big, very steep stream that just doesn't have a lot of water through it. That water is going to run downhill very easily, even though there's not a lot of water. If you have a lot of water, obviously, you'll have more water flowing. So our volt, we can sort of think as like how steep is the stream, and then the amp is how much water is flowing in the stream. It's very scary if you've got both a very steep stream and a lot of water. That's not a river you'd want to cross, except on a bridge.
Which one's the one where, because I remember we talked about it in physics, where the amp could be high, but if the voltage is low, you won't feel a shock?
I think it's if the amps is high, but the volts is low, like it requires a certain amount of volts to go through your body. So like a car battery, and under normal conditions and like with your skin, you're not at risk of being shocked because it's only like 12 volts, even though it can provide a lot of current. If you've got something that's got really high volts, if you've got like 120 volts or 60 volts or whatever amount, that's probably going to travel through your skin, but hopefully it'll be low enough amps that it won't stop your heart.
So the amps is what would stop your heart?
The amps is, my understanding is yes, amps is much more dangerous. There's like lethal zones for amps, but for volts, you could get hit by 120,000 volts, and if the amps is not in that zone, then it's just like whatever. So for the cell that we looked at before with zinc and copper, our standard cell potential is plus 1.10 volts. If we replace the zinc is the one that's giving up the electrons. If we replace the zinc with nickel, Nickel has a lower tendency to give up electrons. So it holds on to its electrons a little more tightly than the zinc does, less likely to be oxidized, and so we get a lower standard cell potential. The forward reaction, nickel metal and copper ion, copper 2 ion, is still positive and it's still spontaneous. It's just not as spontaneous, or it doesn't have as much of a steepness to it, if we're thinking about our river analogy. So one of the takeaways, one of the things that we can pick up here, positive E cell is spontaneous. It produces a voltage. And a negative E cell is non-spontaneous or not spontaneous. So you'd have to put energy in for it to run in the direction as written. If you have a negative cell potential and you flip the equation, then it's a positive E cell, and so it would run, but just in that direction, not in the forward direction the way that it was originally written. But this positive E cell is spontaneous, is important for this chapter. All right, some other parts of our voltaic cell. Again, this is with our little beakers, and we've got a salt bridge, and we've got our electrodes. And we've got a wire. So we're talking now about our electrodes with the green there. Our two types of electrodes are anodes and cathodes. Oxidation occurs at the anode, and reduction occurs at the cathode. And the mnemonic that the book is suggesting is red cat, and that oxidation and anode both start with vowels, and so those should go together. We also know of anions as negative. So if we've got electrons in a negative environment, the electrons are going to be leaving, if they can. They'll try to leave that negative environment because they're getting pushed away, since electrons are also negative. So our electrons leave, and that is oxidation. So if our electrons are flowing left to right here, then this left electrode would be our anode. And our cathode is where our reduction is occurring. We're gaining electrons. So our right electrode here would be our cathode. Again, cations are positive, and so that's where the electrons are going to go. So that's going to draw in or attract electrons. And it will be important to know all of these terms, because you'll have to almost certainly draw out a voltaic cell diagram on an exam. And then one of the other fun, it's not really a mnemonic, I think, but cations are positive. pause being they're biscuit makers. Now, the reason that we have that salt bridge, as mentioned earlier a little bit, is that if we just have electrons flowing in one direction, that's going to cause a buildup of charge in the solutions, because we would just be running electrons from our left solution to our right solution, and over time we've got an excess of electrons in the right solution, and our left solution is going to run out of electrons or run lower on electrons. And so that'll sort of start to cause a buildup of charge. So to keep our charge neutral, we have a salt bridge. So the salt bridge, let me copy this, because I don't want to draw it again. For time reasons, definitely, just for time reasons. So if we don't have a salt bridge, then our charge builds up. We would end up with a negative charge on the right, positive charge on the left. But with a salt bridge, that's this bit in the middle. Our counter ions, our potassium and our nitrate in the example, can flow between the two half cells, and the solutions can't just freely mix with each other. So the zinc and the copper solutions are probably going to stay mostly in their beakers, and we'll just get potassium and nitrate flowing in this inverted U-shaped tube. So in our salt bridge, we would have a buildup of positive charge at our anode. That's where our electrons are leaving, and so our negative ions are going to flow this way. So in the example, this was nitrate. So we've got nitrate flowing towards the positive side, because that would neutralize the charge. And we've got potassium flowing towards the negative side, also to neutralize that charge. So our counter ions flow to neutralize charge caused by flowing electrons, or by electron flow. So a good way to figure out possibly which way our counter ions are flowing, set it up without the salt bridge, and think about, okay, where are the electrons flowing? If the electrons are flowing left to right, the right side is going to end up with a negative charge. The left side is going to end up with a positive charge. Then add the salt bridge in and think, okay, where would the electrons flow to make this balance out? The negative is going to flow to the positive is going to flow to the negative, and that'll help keep things nice and balanced. There are a lot of parts to a voltaic cell. All right, back to our example of the voltaic cell. So we did get it correct. So we have our negatively charged stuff flowing to our anode, our positively charged ions flowing to our cathode because of the way that the electrons are flowing first. So this is probably technically wrong, but it might be a good way of thinking of it. The electrons flow first, and the counter ions respond. To the electrons. In reality, it's probably all happening all at the same time. Questions about voltaic cells so far? All right, in a voltaic cell, which direction do electrons flow? And this was all I had to cover up the diagram that's showing which way they flow. So in a voltaic cell, which direction do electrons flow? Do they flow from higher potential energy to lower potential energy, from the cathode to the anode, or from lower potential energy to higher potential energy?
From lower to higher?
Wouldn't it be the other way, higher to lower, because, what do you call it, the cathode is the one that is.
Yeah, it's from higher potential energy to lower potential energy. And that's from the anode to the cathode. So the B is wrong here because it's the wrong direction. So higher potential energy, if we're thinking about potential energy as our elevations, right, it's going to flow downhill rather than uphill. And the meme, this is my meme, I made this one. I know it's a very dumb meme. The President Garfield, not the person that said, "I hate Mondays," it was the orange cat. It's a fun mix-up. There's some context to it, but I thought it was funny. Anyway, now that we've seen the meme, our flow of electrons is going to flow from high potential energy to low potential energy. So there's the answer. We also have an electrochemical cell notation so that we don't have to draw it out every single time. So this is our line notation. We've got our oxidation half reaction on the left. We've got our reduction half reaction on the right. We've got double lines indicating our salt bridge. Or if you want to think about it, just separating our two solutions. And then we've got single vertical lines that separate phases. If we have multiple species, multiple reactants and products that are, for example, in the aqueous phase, those would just be separated by commas. We'll see some examples of that. So this, as you might be able to guess, is a lot quicker to put together than drawing out the full voltaic cell diagram from earlier. There's also cases where all the principal species in a half reaction are aqueous, and so we can use an inert electrode like platinum Platinum, famously an inert electrode. Also part of why it makes for good jewelry is because it's inert. Doesn't react with stuff. So here's an example of putting together an electrochemical cell notation. So we've got our full equation up top, and we can figure out the things that are involved in our half reactions for oxidation and reduction. They're already broken down below. So our iron is going from 0 for its oxidation number to 2 plus for its oxidation number. That's increasing oxidation number. So we've got our half reaction would be iron metal going to iron 2 plus. And that's our oxidation half reaction. And then all of the other things, except for water, are involved in the reduction half reaction. So our permanganate and our H plus going to manganese 2 plus. We're going from a +7 to a +2. That's a reduction in oxidation number. So that's the other way that we would figure out that it's the reduction half reaction. And since these are all charged, they're all aqueous, and so that's when we invoke our platinum electrode. Because otherwise we wouldn't have a solid state to connect our wire to. And it probably wouldn't be a great idea to just put the wire directly into the solution. Better to have an electrode where the electron interchange can happen. Surface area probably matters to some extent. And here's that example with an inert platinum electrode. So we've got our electrode in our reduction side, since everything here is aqueous. So there's electron exchange happening at the surface of that platinum electrode in the solution. Since our iron is losing electrons, that becomes our anode. Electrons flow from our anode to our cathode, where the electrons can be used in the reduction half reaction, since reduction is gaining electrons. We also have, just for quantification reasons, have, putting a number to things, standard electrode potentials. The standard E cell for an electrochemical cell depends on the half reactions. So the standard cell potential depends on 2 half reactions. If you think about it for long enough, you might realize that this is a little bit problematic for possibly figuring out some of these E cell values. If we wanted to mix and match a lot of different possible anodes and cathodes, we would have to test every single one and figure out, okay, what's the difference between these two? And then test another couple and, okay, what's the difference between these two? And it would end up, we would have to do a lot of this. However, we can also break down a standard electrode potential. So each half cell, we can have a standard electrode potential, and that's much more useful because then we can compare one half cell to another half cell. If we know their two values, we don't have to put them together and measure it. We can just compare the two values in theory and then compare another two and another two and another two. But there's a problem with that we'll talk about a little bit later. So the high potential energy, low potential energy, we would basically be thinking about these as our standard electrode potentials. So how likely is one to lose electrons? How likely is the other to lose electrons? Just comparing the high and low potential energy, these are just relative. So if we've got one that really likes to give up electrons, one that doesn't like to, is more likely to gain electrons, we're going to get a good flow or a good potential energy, a good steepness between those two. And it's great if we can just compare those directly. The problem is the electrode potential in a half cell can't be measured directly. It has to have electrons flowing somewhere. We can't just measure that by itself because the electrons have to go somewhere. It has to have somewhere to give them to. And if we hook it up with another half cell, then there's going to be that difference between those two half cells, and then we're just measuring the difference between those two. So we have to set a baseline. And our baseline is the standard hydrogen electrode. So this is our baseline for measuring cell potential. And then we can compare, or scientists who are coming up with new electrode materials, they can set up or buy a standard hydrogen electrode, compare their electrode to this hydrogen electrode, and get the value for their new electrode. And everyone else in the world will also be using this standard hydrogen electrode if they're trying to compare things. So this gives us a very convenient base point or reference point. So we're using hydrogen gas. It's at a pressure of 1 atmosphere. 1 atmosphere is standard. We also have an H plus solution that's 1 molar. 1 molar is also standard. So these have to be at 1 atmosphere and 1 molar. And since we've got aqueous and gas, we don't have a solid form for hydrogen, we have to use our platinum electrode or some other inert electrode. It wouldn't necessarily have to be platinum. It just has to be something that can live in very acidic conditions. So this is what measuring half cell potential with the standard hydrogen electrode that She would look like. So we've got our standard hydrogen electrode, that's our zero, our baseline, our reference point. And then we've got the thing that we're testing. So our baseline or our reference on the left, and our testing material, I said on the left for the baseline, it's on the right for the baseline. The thing we're testing is on the left. And instead of putting a light bulb in the middle, you would put a voltmeter to measure the difference. And we've got our standard potential for a cell, standard cell potential. It's the difference in voltage between the cathode and the anode, or the final and the initial cell potential. In this case, we've got a value of 0.76. So our measured cell potential is 0.76. It's positive, that means it's spontaneous. In that direction. So we can determine the electrode potential for the zinc and zinc 2+ half cell, our anode, our negative thing. Since we assigned our standard hydrogen electrode our potential of 0. So relative to our standard hydrogen electrode, we've got a value of 0.76. And we get our standard cell potential as negative 0.76 volts. The reason for that, the math, of course, is here. Our cathode was the standard hydrogen electrode. That's the one that was gaining the electrons. And our anode was the one that was losing the electrons. Since we got a positive value, 0 minus positive 7.6 gives us negative 0.76. A negative or more negative means electrons are more strongly repelled, would possibly be one way of thinking of it. I think there's two L's in repelled. And that's sort of written here, more negative electrode potential means greater potential energy of an electron. Greater potential energy, that's like the higher beaker of water, it's going to flow to the lower beaker of water. So it's more likely that electrons will flow from that electrode to the other electrode. More likely to lose, more likely to give up electrons when its standard cell potential is negative. If we measured a copper and a copper 2+ electrode, so looking at a different half cell, our measured standard cell potential is negative 0.34. It's more positive potential than the standard hydrogen electrode. So it's going to send electrons. No, sorry, it's the other direction. It's going to gain electrons. Lower potential energy for an electron is going to not give electrons to the standard hydrogen electrode. And I think there's possibly a number issue here. This might be, I think that's maybe supposed to be positive. Isn't electrochemistry fun? So this is the other side of the coin. The more positive a positive E cell means more likely to gain electrons. So it would be good cathode. I think that's correct. So our copper electrode is positive relative to the standard hydrogen electrode. It's going to tend to draw electrons away from the SHE. Our zinc electrode was negative relative to the SHE, tends to give or repel electrons towards the standard hydrogen electrode. And convention is that we write electrode potentials for reduction half reactions. How likely are they to gain electrons? So for copper, we have a positive 0.34. For zinc, we've got a negative 0.76. And here are some thoughts. When using this standard cell potential is the standard cell potential of the cathode minus standard cell potential of the anode. Can use the cell potentials as listed in table 20.1. Don't spend any of your time memorizing them. The only one that you need to know is the hydrogen one. And that's really easy because that's our baseline. It's 0. Our standard hydrogen electrode is 0. That's the only one that you need to know. So the hydrogen is 0. That'll always fall in the middle on a full table. Otherwise, you'll just be given these. So the hydrogen one is the one you need to know. You can also, instead of using this equation, you can use the half reactions and add the cell potentials. So you're going to flip the positive negative, flip the sign. If you flip the equation. We're not doing anything with coefficients for these. So you're not going to multiply it by 2 or 3 or a half. All that matters is the species. The actual number of things doesn't matter. So an example, this zinc equation, so our zinc reduction half reaction, if we flip it in the other direction, now the E cell is positive 0.76 volts. So that's what the flipping left and right would look like. Or you can use this E cell equation. This is half of the table. So this is all the positive E cell values. It's in your book. It should be 20.1. Or if you've got a different version of the book, it might be slightly different. Whatever this chapter is, it'll be in there. So here's all the positive cell potentials. We've got increased tendency towards gaining electrons as we're moving up this table. So these are all more likely to proceed in this direction. They've got positive E cell values. And then here's the other half of the table. So this is our hydrogen baseline, our reference point. Everything below this is more likely to lose electrons, a higher tendency towards oxidation. So lithium is more likely to go to lithium plus, and an electron, that would have a positive 3.04. Much more likely to give up an electron than it is to gain an electron. Which makes sense, it's a metal. If we look at the very top of our reduction half reactions, fluorine much more likely to gain an electron and become F-. We probably could have guessed that from previous chemistry experience. So it makes sense that it would be kind of up here. It's got a super high electronegativity value. It's really close to having that neon noble gas configuration. So there's some things that we can do to work out kind of what these things mean. We know that fluorine's likely to pick up an electron. It's really close. It's a halogen. It's close to being a noble gas configuration. It's really going to want to pick up an electron. Very likely to move in this direction. All right, so some standard electrode potential summary. The big one to know, the electrode potential of the standard hydrogen electrode is exactly 0. Our relevant standard states, or standard conditions, are 1 molar, 1 atmosphere. The electrode with the greater tendency towards reduction, gaining electrons, is positive. Its E cell is positive. A positive value will attract electrons, just like a positive charge will attract electrons. The electrode with less tendency towards reduction, so more likely to oxidize, is negative relative to the standard hydrogen electrode. Negative will repel electrons. And our cell potential is the difference between the electrode potentials of the cathode and the anode. We need a negative in here because one of them is going to flip. That's going to be the anode. It's the one that's going to flip. Anode is oxidation, is losing electrons. We've written them in the reduction form. So the oxidation one we flip.
If we didn't flip it, we just plugged it in, it would still be positive because of that minus, right? Because our anode is negative.
That's why we have the minus there, yes,
Yeah.
is to account for, basically to take into consideration that we should be flipping it, the negative's there to do that for us.
Okay.
So you don't have to flip it before you put it in, you just put in the standard cell potentials.
If we use it, we don't flip. And
Correct.
if we don't want to use it, we flip.
Right.
Okay.
And a positive value, positive E cell is spontaneous electrons flow. So it could be used as a battery. If you calculate a negative E cell, it's not spontaneous. You can get it to run in that direction, but you will have to put in electrons. You will have to put in energy for it to move in that direction. Okay, and we will use some tabulated standard electrode potentials. So we're going to calculate a standard cell potential for this electrochemical cell. We've got lead 2+ and chromium going to lead metal and chromium 3+, trivalent chromium. So relevant information that we need from this is our table 20.1. So let's find lead and lead 2+ and chromium 3+. I'll just scroll back. Okay, looking for lead and lead 2+ or chromium. I think they're both on this negative one. So we've got chromium 3+ going to chromium metal. So that's one of the ones that we need. We've got a negative 0.73. And we've got lead 2+ going to lead, and that's a negative 0.13. So lead 0.13, chromium 0.73. Negative 0.13, and for chromium, to chromium metal, it's negative 0.73. As the reaction is written out, the lead 2+ is on the left. That's the way that we currently have it written out for our lead. So that one's correct as written. The other one we would need to flip. So that would flip to become chromium going to Cr3+ plus 3 electrons. And then we would multiply them by a certain, coefficients. But the end result is we've got a positive 0.733, not 7. So if we add these up, (0.73) plus negative 0.13, we get a value of 0.6. So that's the way that I would do it. We could also do it with that equation. This one, cathode minus anode. The cathode is more positive. That's going to be our minus 0.13 minus negative 0.73. So we get minus 0.13 plus 0.73 or 0.60. Anode does oxidation. It's more negative, more likely to lose electrons. The more negative value is more likely to lose electrons, so that is how we get chromium as our anode. The lead is the more positive value. Cations are positive. The cathode is positive. Since it's more positive, it's gaining electrons. So it's sort of the reduction reaction. Questions? Cool. We will pick up just after this next class.